Welcome to the Virtual Institute. Last time we have discussed different terminologies and different forms of energy which are necessary to understand before going through the subject of heat transfer. We have applied energy balance over the closed as well as open system. Today we will go through overview of the different modes of heat transfer. We will cover only overview in this lecture. In more depth, we will cover each mode of heat transfer in the preceding lectures. Let's start from conduction, which is the mode of heat transfer. Conduction can occur in solids as well as liquid. Conduction heat transfer involves no movement of the molecules from one place to the other place. The molecules do not leave their position in the object through which heat transfer is going to take place. For example, we have a cup of hot coffee and we want to stir this coffee using a spoon, and after some time this cold end of the spoon will get warm and we will feel hot. This is because of the transfer of energy from this part of the spoon to this colder part of the spoon. The molecules collide with higher energy at this part and with the neighboring molecules in the spoon, and ultimately this heat goes on transferring from this hot part of the spoon to the colder part. In the same way, during winters, we have heated room. For example, by use of an electric heater, we have this room, but there is cold air present outside the room. There can be a loss of heat through these walls of the room from hot inside air to the cold outside air. This is because of the conduction. This loss of heat is due to the conduction. Remember that in conduction, the molecules of the body do not leave their place. They do not leave their position. They just go on colliding with the neighboring molecules, transfer their energy, and the neighboring molecules which get energy on collision, they in turn transfer to the further neighboring molecules. In this way, heat goes on transferring from hotter part of the body to the colder part. Conduction can occur in solids, liquids as well as in gases. In solids, conduction can occur by two mechanisms. One is due to lattice vibration. The molecules at the hotter part of the body are more energetic. They collide with the molecules which are less energetic and they transfer energy to the less energetic molecules. The less energetic molecules in turn transfer the energy on collision with the neighboring molecules. In this way, energy as well as temperature goes on transferring. In this way, heat transfer takes place from higher temperature to the lower temperature, or from the molecules at higher energy to the molecules at lower energy of the body. This is called lattice vibration. In solids, heat transfer through conduction can also occur by movement of the electrons. This mode of heat transfer is more prominent in metals where free electrons are present. The free electrons start floating from one part of the metal to the other part. In this way, heat is transferred. So, heat transfer in solids can occur by two mechanisms. One is lattice vibration and other is the movement of free electrons. Heat transfer through conduction can also occur in liquids as well as gases. For example, in gases, heat transfer occurs through the diffusion of energy. For example, we have a hot plate here at temperature T1, that is, and a cold plate here at temperature T2, and T1 is more than T2. There are molecules of gas present between the plates. The molecules present close to the hot plate are at higher temperature, and they have energy more than those molecules which are present over the cold plate. These molecules have high energy, therefore they collide with the neighboring molecules of low energy and transfer their energies to the neighboring molecules. These molecules can have rotational, vibrational, as well as translational movements. Therefore, these molecules have rotational kinetic energy, vibrational kinetic energy, and translational kinetic energy. On collision with the neighboring molecules, they transfer their kinetic energy to the molecules of less energy. In this way, heat transfer occurs from high temperature to the low temperature in the gases. The gases, these molecules do not leave their place. They do not actually leave the position. This does not happen that these molecules will leave its place and come to this plate. If this happens, then there will be no conduction. If it only collide with the neighboring molecules and transfer its energy to the neighboring molecules, and its mean position is almost the same, then this phenomena is conduction in gases. The temperature profile of this transfer of energy from high temperature to the low temperature in the gas, from this plate, hot plate at temperature T1 to the cold plate at temperature T2 is like this. This is temperature axis. This is temperature axis, and this is position or distance axis from hot plate to the cold plate. Molecules at high temperature T1 transfer energy to the molecules at low temperature T2. The temperature profile is like this. And the distance it covers between both plates is x, this distance. This distance is x. Heat transfer by conduction in the liquids is also almost through the same mechanism, except that in liquids the spaces between the molecules are very less as compared to the gases. Also in liquids, the intermolecular forces are comparatively strong. The rate heat equation for conduction can be written, which was rate equation. Rate equation for conduction is the equation presented by Fourier, also called Fourier law. If we have a wall of thickness x, if this face is at temperature T1 and this space is at temperature T2, where T1 is greater than T2, and if heat transfer to the wall Q in kilojoule per second is the Q, then according to Fourier's law, the rate of heat transfer Q is proportional to the area perpendicular to the direction of flow of heat, this area. And also the rate of heat transfer is proportional to the temperature gradient dt over dx. The proportionality constant is the property of the material through which heat is going to be transferred, that is K, also called thermal conductivity. Here we write negative of the temperature gradient because heat transfer occurs from high temperature to the lower temperature. In other words, heat transfer occurs in the direction of decreasing temperature. That's why the temperature gradient is negative. In heat transfer subject, we define Q as energy per unit time. Joule per second, that is watt. And we define Q prime as energy per unit time per unit length. We define Q double prime energy per unit time per unit area perpendicular direction of flow. This is also called heat flux. Energy per unit time per unit area is energy flux or heat flux. Another term Q triple prime, that is energy per unit volume, but that is very rarely used in the subject of heat transfer. There are some assumptions of Fourier law. First assumption is that the temperature of the phases should be constant. If there is a T1 temperature at the start of heat transfer and T2 temperature at the start of heat transfer of the phase 1 and phase 2, then there should be same temperature T1 and T2 at the end of heat transfer. It means that the heat transfer should be through the phases which are isothermal. In other ways, we can explain this in such that the phase should have heat sink as well as heat source. The phase that is at a higher temperature, that should have a heat source. That's why it will be maintained at higher temperature during the process of heat transfer. The phase that is at lower temperature, that should have heat sink. That's why it will be maintained at lower temperature during the process of heat transfer. Otherwise, temperature of the phase will be reduced if we do not have heat source or sink. So first assumption of Fourier law is the phases should be isothermal. Second assumption of the Fourier law is that there should be steady state heat transfer. Third assumption is that there should be unidirectional heat transfer or one-dimensional heat transfer. In this example, we have seen that heat transfer occurs only in x direction. We have neglected y and z direction of heat transfer. This is the assumption of Fourier's law. Another assumption of Fourier's law is there should be constant temperature gradient. Because we have defined the both phases to be isothermal, that's why dt should be constant and dx is also constant, which is the thickness of material. That's why temperature gradient should be constant. There should be no heat of generation. Q generation should be equal to 0 for Fourier's law. These are the assumptions of Fourier's law. And last assumption is that the material should be isotropic. It means thermal conductivity of the material should be constant in any direction. In x direction, y direction, as well as z direction. The thermal conductivity should be constant. An important concept is the thermal resistance. When we define Fourier's law, we should also define thermal resistance, and this is the important concept which is necessary to understand for solution of some practical problems. So, for conduction, before defining thermal resistance, we should first review flow of electricity through a conductor, which is defined by Ohm's law, that V is equal to I into R. V is the difference in voltage, I is the current, R is the resistance of the electrical conductor, and R is equals to voltage drop V divided by flow of electricity, that is the current I. Now, heat transfer is analogous to electricity flow. It means flow of heat transfer can be explained in the same way as the flow of electricity. Flow of electricity is explained by Ohm's law, whereas flow of heat transfer through conduction is explained by Fourier law. We have seen this already. And Fourier law states that Q, heat flow, is equal to minus K A dt over dx. Or Q is equal to dt over dx divided by Ka minus dt is the temperature drop across the faces of the wall through which heat transfer by conduction is going to take place. Dx over Ka is the thermal resistance. Like in electricity, current I is equal to voltage drop divided by electrical resistance. In the same way, in the heat flow is equals to temperature drop divided by thermal resistance. That's why we say that flow of heat and flow of electricity is analogous. So there is analogy between the heat flow and electricity flow. Another important concept related to thermal resistance is the contact resistance. When two layers of an object are combined with each other, a resistance is developed at the interface of the two layers. For example, object A and object B are combined with each other. A resistance is developed at this interface of the objects. This resistance is called contact resistance. And because of this resistance, there will be significant drop in temperature. Therefore, rate of heat transfer will be affected because of the contact resistance. That's why it is very important to consider the contact resistance in calculations of heat transfer. We will see this in the exercise on solution of the problems. There will be a temperature drop and the temperature profile will look like this. This is X and this is T. This is T1, this is T2, and this can be a T prime. This is between T1 and T2, and there is a sharp reduction in the temperature at the interface. That's why rate of heat transfer will also be affected adversely because of the presence of interface resistance, that is also called contact resistance. Second mode of heat transfer is convection. Convection is the mode of heat transfer in which molecules of the object leave their position and transfer the heat. There is a physical movement of the molecules of the object, which is very significant movement. So that's why we call that the molecules are leaving their position. On leaving the position, the molecules transfer heat to the colder part of the object. Heat transfer through convection can occur either by natural convection or by forced convection. If we have tank where a liquid is filled inside the tank and we have a heating coil for heating the liquid of the tank, the molecules at the hot surface of the coil will get heat and the density of the molecule will reduce. Therefore, the molecule will float to the surface. In this way, heat transfer occurs because of the density difference and because of the buoyant forces, movement of the molecules occurs. Therefore, molecules leave their original position from hot surface of the coil to the top colder surface of the liquid. In this way, molecules leave their position and get heated up. This is called natural convection. If we place some mixture here, by the use of a mixture, there will be also movement of the molecules and the molecules get heated up on striking against the hot surface. The additional force required to move the molecules make the convection process forced. That's why this convection is called forced convection. Therefore, in forced convection, an external power like external agency like fan, pump or a mixture is required for the heat transfer to occur. While in natural convection, only the density difference of the molecules is sufficient for the convection to occur. In case of forced convection, molecules move at more speed. That's why convection rate heat transfer is more fast. In case of natural convection, only density difference results in the transfer of heat and transfer of molecules from colder part to the hot part of the body. That's why the convection process is very slow in natural convection. Assume a hot plate over which molecules of the gas are moving. There will be a velocity gradient. Velocity of the molecules intact with the surface is low, and this velocity goes on increasing as we move from surface of the hot plate to the center of the pipe or to the center between the both plates. The velocity of the gas intact with the surface is low and the velocity at the center between the both plates is maximum. Therefore, a velocity profile is created here. In the same way, temperature of the gas at the surface of the hot plate is high and temperature of the gas away from the surface is low, and this temperature goes on decreasing. Eventually, this is minimum at the center. Therefore, a temperature profile is created here. This is the temperature profile. Temperature, if this is T1, this is T2, then T1 is greater than T2. Here is velocity profile. We normally define temperature at the center of the pi part between both plates to be infinity, and temperature of the hot plate T1 as Ts, the temperature at the surface. The layers of gas intact with the surface has very low velocity, and the layers of gas next to this layer has higher velocity. Therefore, it exerts force on the slow moving layer in the forward direction. Also results in transfer of temperature because the temperature of the layer intact with the surface of the hot plate is high. It means high moving layer of the gas result in transfer of temperature from the hot surface of the plate to the center between the both plates. In this way, heat transfer occurs by forced convection from hot surface to outside the boundary layer. Because this layer exerts force on slow moving layer and ultimately make it move out of the boundary layer. Therefore, it also results in transfer of temperature out of the boundary layer. In this way, heat transfer occurs from high temperature to the lower temperature. This is the result of forced convection. However, at the surface where the velocity is very small, that approaches to zero, in this place, heat transfer called energy diffusion occurs. Therefore, heat transfer through energy diffusion occurs only in the layer which is at very lower velocity, and this heat diffusion is only because of the collision of the molecules. Heat transfer by convection is governed by Newton's law of cooling. Like heat transfer by conduction is governed by Fourier law, the same way heat transfer by convection is governed by Newton's law of cooling, that is Q is equal to A H Ts minus T infinity. Rate of heat transfer is proportional to area through which heat transfer occurs and the temperature gradient across this fluid or across this film. Normally Q over A is written as the heat flux Q double prime is equal to H, which is the heat transfer coefficient, S minus T alpha. In other words, Q is equals to Ts minus T infinity divided by 1 over HA. Again, comparing this equation with the flow of electricity, we realize that this is temperature difference, temperature drop, and this is the convective resistance. Heat transfer by phase change also occurs due to convection, because during phase change there is either boiling or there is condensation. During boiling, the vapor rises and vapor leave the surface of the liquid. Since the vapor leave their position, that's why there is a convection heat transfer. During condensation, the vapors leave the body of the vapor and become part of the body of the liquid during condensation. That's why heat transfer during condensation is by convection.